So now I've got a couple of exercise questions for you. The first one basically says, does this configuration look okay? We've got net A, net B, net C, and another net A over here. Remember, we can artificially create subnetworks, so I partitioned net A into 2 different networks. But this is not a valid configuration because you can see border node 3 has connections to 2 different network nodes down here in net B, and both of those network nodes are not border nodes, which means we've got 2 peripheral boundaries coming into the same network, and that is not allowed by the architecture. All right? You can bring up the configuration, it just may not work all the time, that's all. And it'll break when you least desire. All right, how about this one? I decided to break net B up into 2 different net Bs and let this guy have a peripheral network boundary down to each one of the 2. That one kind of looks like it's valid because it looks like we've only got one connection into each of these 2 networks down here, but in fact this is not a valid configuration either, because even though there's only one path, peripheral node path, into this guy from BN3, there's also a way into this network from BN6. There are 2 ways into this net B also, through BN3 and also through BN4. So when I said no alternate paths into this network, I meant absolutely none. It really, you gotta kill these links so it's obvious that there's only one way to get into these subnetworks, and that's through these 2 nodes or through these 2 nodes. That's basically the limitations that you have on peripheral network boundaries. Because of these restrictions, I'm pretty sure that nobody is really going to want to use peripheral boundaries if they can all help it. So again, my suggestion is if the adjacent non-native network node happens to be a VTM, it's best to configure him as a border node. All right, so the next question we have about extended network boundaries is how do we create extended network boundaries, border node boundaries, that support the SSE function, Session Services Extensions. The rules that we talked about before, the owning control points and their network node servers, still holds. But now it holds for every subnetwork along the session sender path. So in the OLU network, the CP of the OLU and the NNS OLU have to support the function, has to support the NNS. In the intermediate node, the extended border node where you is the NNS OLU, and border node on the exit side is the NNS. Because the border node function is built on top of the SSE function, the border node automatically supports SSE. So from here over, everything looks fine, assuming it supports SSE, and so does that guy. On this side over here, on the other hand, we've got a peripheral network node, the network node server of the DLU in the OLU's network. So now the ability to start an SSE session from the OLU over here to the DLU over here kind of depends on whether this network node here supports SSE. If it's a base network node, you're out of luck. If it happens to be a VTM, then it would work. Remember, not all peripheral boundaries support the SSE function. It depends on the capability of that non-native network node. Okay? We got a couple of more charts in here on extended border node. The first one is, how do you do extended border node with DLUR, DLUS? Many customers may not realize this, but the DLUR and the DLUS nodes do not have to be in the same APPN topology subnetwork. They can actually be in different APPN topology subnetworks. And so I drew a picture where something like that might occur. Notice for my only peripheral boundary now, I've got a dashed line. This dashed line is never activated as long as that one is, so there's only one path into here. Okay, but I have a full boundary there for a reason. And I want to show you where the peripheral boundaries can be on DLUR, DLUS path, and where the extended boundaries have to be on the DLUR, DLUS path. So when we talk about the DLUR and the DLUS, we're really talking about 3 different nodes. The DLUS is the guy who controls the secondary LU, but the DLUR is the actual guy who attaches the dependent LU. And then the third node that we have to think about is the node where the primary LU is. That's the guy that the SLU wants to actually start a session with. There are 3 paths that we have to talk about. The first one is the DLUR path. That's the path over which we're going to start a special set of LU62 sessions, the CP Server Manager sessions. And on the DLUR to DLUS path, in this case, for example, I'm going to use this one here, or maybe I'll use this path over here, from BN1, BN3, BN4, and then down to the network node. That's my DLUS to DLUR path. Peripheral network boundary is allowed on the DLUR to DLUS path. It has to be the network boundary that's closest to the DLUR, and the border node has to be on the DLUS side of that boundary. So when we're talking about the first one, this is an extended boundary, it works fine. This is an extended boundary, it works fine. So this DLUR, DLUS session works perfectly. In the other case, we're going to go this way. This is an extended boundary, so that works fine. This is a peripheral boundary, but it's a peripheral boundary closest, it's the boundary closest to the DLUR, and the border node is on the DLUS side of that peripheral boundary. So this one over here works also. Those are the restrictions that you have on the CP Server Manager session path. There's also the path that the DLUS to PLU path. since the DLUS responds on behalf of secondary L users come in, it's the DLUS and the PLU node that actually communicate to establish the session, to calculate the path, and then to tell the PLU where to send the bind. On the DLUS to PLU path, which is the APPN locate path, all of the boundaries that you cross have to be extended network boundaries. There has to be a border node on both sides. Even if you've got a peripheral network node that supports the SSE function, you still have to have extended boundaries everywhere along the session path, along the DLUS to PLU path, that is. Now the PLU to the DLUR path is the path that the actual bind is going to take. We certainly don't want the PLU's bind to have to go up into the DLUS node and then come back down again. We'd rather the PLU's bind go directly down to the DLUR where the DLUS attaches. And so the same restrictions basically exist on the PLU to DLUR path, which is the actual LU session path. The same restrictions exist that exist on the DLUS to DLUR path. You're allowed one peripheral boundary. The peripheral boundary has to be the boundary that's closest to the DLUR node, and the border node has to be on the PLU side of the DLUS boundary. The PLU side of the peripheral network boundary. Finally, I've got a chart here on global connection networks. We've talked about virtual routing nodes before and the ability to create networks where you get mesh connectivity without having to predefine things, and you predefine a lot of links, and you eliminate a lot of the intermediate routing that goes on. In this particular case, what we're trying to do is invent an architecture that allows us to use a virtual routing node to circumvent the border nodes. We found out that when we started sessions from one network into another network or across two networks, the border nodes in those networks were always part of the session path. And even if you did HPR end-to-end, you'd still have a lot of ANR traffic flowing through those network nodes as just ANR traffic. And we found out that if you had enough of those sessions, it's possible that the border nodes could become a performance bottleneck for sessions that cross network boundaries. So what we decided to do was invent a global VRN architecture that allows nodes from different networks to define a link to the same global virtual routing node. And if you code it with VN type equals global so that we know it's global, we'll pass information about the overruling network's connectivity to the global VRN over to, for example, the destination networks, so that when he calculates the route, they can see that both of these nodes are attached to the same global VRN and calculate a route that circumvents one or both of the border nodes, or all of the border nodes if there happen to be more of them on there. So global VRNs are implemented as enterprise extender only. It's a connection network that's allowed to cross sub-network boundaries and allows those cross sub-network sessions to avoid the potential bottleneck of sending every session through border nodes. There are several restrictions now on the use of global connection networks. First of all, you have to have extended network boundaries along the entire session path, or else global connection network is not going to work. There's no restriction about that at all. Second of all, it's only used between the OLU and the DLU network. If I'm trying to start a session from net C over here to net A, I will not use a global connection network into the intermediate network and then route myself over the rest of the way. I will basically use the border node path to get all the way over there. But if my OLU network searches up to here and then comes down to net B, both of these are on the VRN, I could then actually use the GVRN to circumvent going through net A. So even though the search went through net A, the session path would not have to go through net A. So again, we only use GVRN between the OLU and the DLU subnetworks. We will not plop into a GVRN and use it into an intermediate network. We also will not use global VRNs if either the OLU or the DLU is in subarea, which means you're crossing an interchange node into the subarea network. So in that case, you basically are going to go through the border nodes as well. We've noticed now that once you've got those RTP pipes up through the border node paths, once they're up, when you path switch them, they can actually go across the virtual routing node. So, but when they're initially established, they're definitely going to go through the border nodes at least the first time, if either the OLU or the DLU is considered in subarea. You can exploit global VRNs via every branch extender. You can use them at the branch extender, but you can't use them down inside the branch itself. You can't use them to get around a branch extender. And also, we added support later that allowed you to define as many EE VRNs, IPv4 or IPv6 as you want. We also added support that would allow firewalls to work by passing host names instead of IP addresses in these vectors. So we basically gave you a lot more flexibility in the number and type of virtual routing nodes that you define, as long as you're using the EE version of them, the EE connection network version of them. All right? That is the end of this presentation. I hope you enjoyed it, and we'll see you next time when you see the next presentation.